In this video, we're going to take a look at Dijkstra's algorithm, which is another one of our shortest path algorithms that will give us the shortest paths from a source to all the vertices in a given graph. Dijkstra's algorithm is going to work pretty similarly to Prim's algorithm. Basically, it's going to maintain a type of tree that we're going to call a shortest path tree. And what that does is it basically will tell you the shortest path from the given source, where the given source is the root of the tree. We're basically going to maintain two sets as we iterate through our graph. One set is going to be the vertices that are in that shortest path tree. The other set will be vertices not yet in the shortest path tree. And basically on each iteration of the algorithm, we just find the vertex that hasn't been included yet with the minimum distance from the source. We then include it, and that's going to end up billing us out the minimum path between our source and any other node inside of our graph. The process for this is basically done as follows. We have our setup for our graph first off, and the setup is basically going to be like a modified adjacency list where, all of the columns and rows are indicating edges between the different vertices. So in this example here, what we're saying is that there exists an edge between 0 and itself, and it has a weight of 1. Here we're saying that there is an edge between 0 and 1, and it has a weight of 4, right? Here we're saying that there's a vertex between, or an edge between 0 and 2 that has a weight of 2, right? And similarly, this would be at 1, 0, so between 1 and 0, there's an edge with a weight of 4. Between 1 and 1 itself, right, there's a weight of 4. And then between 1 and 2, there is a vertex edge with a weight of 8, right? So we're just indicating the weight for each edge when one exists. And that is going to be the general way that we're going to structure out our adjacency matrix in this case. We pass that into our graph as well as the number of vertices that our graph has. And then from here, we're just going to need one simple little helper function, which is min distance. And it's going to take in the distance list or array that we have, as well as this SPT set, which is going to be this shortest path spanning tree. And for now, I'll leave it as is, and we'll just start with our implementation of Dijkstra, and it will make sense where this fits in as we go. We're going to start by assuming, like in our Bellman-Ford algorithm, that the distance for every single node is going to be equal to the maximum size possible times the number of vertices that we have, right? From here, like before, we update the source to be 0, since the distance from a source to itself would be generally 0. And then we move into our SPT set, which is going to have a false for each of our vertices to start. This is indicating what things are inside of my SPT currently. That is the shortest path tree that we're building. Then for all of the different i's in range of the vertices that we have, so for all the vertices that we have in our graph, we're going to compute what has the minimum distance currently with this distance and SPT set provided. The way that we calculate this is generally we're going to start by assuming that the minimum is the value at index 0. We're going to keep track of its value as well as its min index, and then I'm going to iterate through for all of the vertices, and I'm going to check to see if the distance at a vertex v is less than the min, and it's not in the SPT set currently. So if it's not in the SPT set, and it's a smaller possible value, we're going to assign the minimum to be that value and keep track of min index, setting it equal to that index. At the end of all of this, we're simply just going to return back whatever that min index ended up being, right? So that just finds the minimum possible value out of the set that's not currently inside of the SPT. From here, what we do is we set that value, the minimum value, to be true, saying that we're including it in the SPT set. Then I'm going to go ahead and iterate through my different vertices once again. And what I'm going to do in each iteration here is I'm going to check to see if the value at uv is greater than 0, and it's not in the SPT set, and the distance from v is greater than the distance from u plus self.edges at u v. This generally should look pretty familiar. It's very similar to the Bellman-Ford comparison that we were doing, right? It's taking a look at the distance of v and just checking to see if it's larger than the distance from u plus the edge between u and v. If these conditions are satisfied, then we're going to update the distance of v to be the distance of u plus self.edges at u v. So basically, if the value is actually smaller, right, then we actually take that value and update it for distance of v. From here, we simply just return back distance, and we're done. So it's a fairly simplistic algorithm. Still generally going to be OV squared, just like Bellman-Ford. Main difference being that this doesn't work with negative edges, whereas Bellman-Ford generally does work with negative edges, right? But we do still have that v squared because we have these two nested loops, each of them going through self.v, right? So those are the main ideas here. Just to show that this generally does work, we take this graph here, we can run it through from a source of 0 as an example. And when we actually do that, what we'll find is that we get 0, 4, and 2. So the distance from 0 to itself is, of course, 0. The distance from 0 to 1 is going to be 4. We see that we have a direct edge from 0 to 1. That gives us a value of 4. The distance from 0 to 2 is generally going to be 2 because, again, we have a direct edge between those two possible values. Now, if I were to remove that direct edge, you'll see that these values are generally going to change based on that, right? Or if we make this value, particularly large, we may see some differences based on those particular values. But generally, we'll see that those will generally expand and contract just based on the values that are provided in and change based on the different, sets of data that we are providing. So this is an example of how to implement our Dijkstra's algorithm for shortest path between various different nodes in our graph. So thanks so much for watching. I'll see you in the next video.